Recorded is rolling. It is Wednesday, January 28th. So, gonna continue with simple harmonic motion. I got some posters here. I got some demos for you guys. AP used to ask questions about waves. They dropped that a few years ago, but I'll show you guys a little bit about waves because I think it's good to know how those work. Some classic examples. Right? I was hoping to get to some textbook puzzles today. Wasn't able to earlier today, so we probably won't do that. Okay. You guys, what do you have to have done by the time you guys come to class next Wednesday? Yeah, AP classroom, unit 7. Okay, so actually, probably a lot of those you can answer already because you guys completed the pendulum lab and we went through the answers there. So here, I'm gonna give you guys a review of some things you guys saw yesterday, right? And then I'll pick up from there and continue on. Right, so you guys did this whole elaborate lab where you're figuring out what's going to govern the motion of this pendulum. How much time does it take this swing back and forth? Okay. Right. What does it have to do with this angle, this mass, this length? And look, there's also gravity fields is an aspect too. It could be a variable. Okay. So let's go through some. Because what if you start off with this as your pendulum bob, swing back and forth? It takes some amount of time. Okay, so it takes some time. And then what I'm going to do is I'm going to replace this with this one, which let's say it's like 10 times massive. Because if it's 10 times the mass, what happens to the time period? It's the same. It's the same. Okay, because time period is not part of the equation. Okay. What if I make this angle 10 degrees and I let it swing back and forth for 10 degrees? Then I double that to 20 degrees. What happens to the time period? It's the same time period. Okay, just like it's all your left. So, what about this? What if I have a pendulum some length? Right, say 10 centimeters. And I make it 9 times as long. Guys, 9 times as long is how many times the time? 3 times, because it'd be a square root of a factor of 9 right here, wouldn't it be? Something like that. What if I take this pendulum to a planet with a really weak gravity field? What happens to the comparative time period? Bigger. Yeah, it gets a lot bigger. Because if you divide by a small number, doesn't make the overall fraction very, very big. Right? You try it out with the calculator, right? But like on Earth, maybe it's like swing, swing, swing. Then you go to the moon with very weak gravity, maybe it's like takes a lot more time to swing back and forth on the moon. That. Okay. All right, what else would you do with this? Here's pretty close to the lab table you guys had, something like that. We created all these graphs, right? All these graphs to know all these graph relationships. With all these. Okay. Now, AP really likes linearization, especially on the free response question they're going to do with some kind of experimental design. Okay. You have to linearize a graph with some variables. Okay. This is time squared versus length. That's one way to linearize it. Okay. There's other ways too. Okay. I talked about this one a little bit yesterday, but AP only asked about pocket pendulums, so I probably won't go this deep. Okay. Right. Guys, an upcoming lab. Guys, pretty soon. Look for this one pretty soon. I give you guys some long weights and a spring. Okay. And it turns out the time for this to oscillate looks really similar formula to the pendulum. Okay. Actually, here, guys, didn't we circle these yesterday? Okay. So these 5 formulas are going to show up in this unit. Actually, guys, I bet you can answer all your AP classroom questions with just these 5 pictures right here. Actually, these last two are kind of the same thing. They just switch sine with cosine. Okay, but okay. Actually, while I'm holding this in front of the camera, how do you read this top one? What does this say? Yeah, time period is 1 over frequency. Okay, see that? Time period is 1 over frequency. Okay. So, for example, here, let's go back to, yeah. Actually, yes. Hold on to that idea. We'll get that. Okay. Then here's your spring formula, and here's the pendulum formula. They're very, very similar. Okay. And then I'm trying to build up to these sine and cosine curves, which you guys just saw the tail end of class yesterday, and then the bells ring, so we're good there. Right, but let's put a block on a spring and let it oscillate. Now you're going to get to have all these materials in your hands sometime pretty soon, so you'll see this play out. Let's see if you can predict, because I'm giving away the answer right here. I'm telling you the formula. Okay, is what if I replace a small mass with a bigger mass that's 9 times as much? Because if it's 9 times the mass, what happens to the time period? 3 times as much. So maybe the small one's like, maybe the big one's like, takes 3 times the time. Get that? Because a factor of 9 on that end, square root, said 3 times the time. Okay. Because what does the K stand for? Spring constant. Constant's the spring. So here I got a couple of springs. The spring's pretty loose. The spring, really stiff spring right here. So what if I hang the same type lab mouse on each one of these? Okay. Guys, which one of these would take more time to cycle through? It's oscillating more slowly. The really stiff spring or the really loose spring? I bet the really tight spring looks like this. If I hang this on here and hang this vertical and then give it a little stretch right here, let go. But the tight spring's like. I bet the really loose spring is more like. You guys think so? So what it just says, if you increase this K, or sorry, decrease this K, going from the yellow to the brown here, I made the K smaller, didn't I? Okay. And if you divide by smaller numbers, doesn't that give you a larger overall fraction? Takes more time. Okay, guess it. That makes sense. All right. I'll give you guys a lab table pretty soon. It looks fairly similar to this. Have you guys record a bunch of things, calculate a bunch of things. Okay. And we're going to put these type graphs together. Okay. So we'll be looking at these relationships. Okay. I have a poster just for this one that we'll look at in a few minutes. Right. This one at the bottom right, I'm building up to, of course, these curves. I'm trying to get to these curves and tell you guys more about those. That looks a lot like this. This could be position versus time, couldn't it? Right? Like if you have a block on a spring, you pull it down, you say what is its height as a function of time, get it oscillate just like this, right? So move up to that, right? But let's take a few minutes. I'm gonna take a few minutes. Okay, everybody has paper out, right? Okay. So we're gonna do one that's kind of related to this. Actually, I might even do the pendulum version. But here's the principle, huh?
Is it puzzle or just notes?
It's just notes. I'm just gonna make up something. But do you guys see here? This graph is linearized. Now, yesterday you guys also linearized a graph. Okay? And see, I got these weird manipulated axes, like 2 pi quantity squared times mass, and then I have the time squared on this other axis. Okay? And somehow this linearizes, and it looks like the slope will tell you the spring constant. Now, when you guys eventually do this lab, I want you guys to figure that out from scratch and give away the answer here. Okay? But let's go back to something that you guys are familiar with, which is pendulums. Okay? So, maybe somebody's memorized it by now. I don't know. Guys, what is the time period for a pendulum? 2 pi. Yeah, 2 pi squared root L over G. Just like that. Okay. Now, here's a scenario. Suppose you're on some planet. I'm going to say, what is the gravity field? What is the gravity field of the planet? And I'm going to walk you guys through a process that would probably be how AP would pitch you this question, okay? Which is that, all right, so everybody's writing this down, right?
Yeah.
Okay. They would probably give you a table of values. Guys, everybody make a 4-column table. You guys got 4 columns? 1, 2, 3, 4? Okay. All right, so they'll give you different length pendulums. Let's put this in meters, just keeping in base SI units. And they'll say, hey, let's say you take out a stopwatch and you measure how much time does it take in seconds to oscillate. Maybe like 3 and take an average or something. Oh, what? And then 2 more columns, but we'll come back to those later. So let's have the length of the pendulum be like 10 centimeters. Guys, 10 centimeters. How many meters is that?
0.1.
Yeah, 0.1. Okay. And then maybe you have some other pendulums. So that's your shortest pendulum. But then you have a pendulum that's 20 centimeters, so we'll call it 0.20 meters. And then 0.30 meters, 0.40 meters, 0.50 meters. Right? So that this last one would be half of a meter stick long, wouldn't it? Okay. And give you guys a little visual. So you set up this pendulum, has some length L. It's going to swing back and forth. Swing, swing, swing. It takes some time to swing back and forth. Okay. Let you guys catch up to that. And let's say the time that it takes for the short pendulum to oscillate back and forth was like 0.84 seconds. And then you break up the 20 centimeter long pendulum, and that takes 1.19 seconds to cycle for a time period. Then the 30 centimeter long pendulum takes about 1.45 seconds. Then the 40 centimeter pendulum, 1.68 seconds. Then the half meter long pendulum takes 1.88 seconds to oscillate. Okay. Now, there's some way you can take this data and find the gravity field of the planet. Now, if you're thinking algebraically, you might say, well, couldn't I just take any one of these and just plug into this formula and solve for G? I mean, you could do that. Okay. But AP will probably want you to take this whole table of data and turn this into a graph, make this a graph. Okay? And what we're solving for is G. There's some way we can it can show up in the slope of the line, right? And there's a few different ways to do this, and they would accept a number of answers. Okay? But we somehow got to get this gravity field representing the slope of some straight line. Okay? Okay, now I'm going to take this equation that you guys told me, it's straight off AP equation B, okay? And I'm going to rearrange it a little bit so that you can linearize this. Oh. And I want it in the form like y equals mx. I'll go ahead and write that. Y equals mx. Y equals mx plus b. You guys get that? Okay. So this m refers to the slope. I'm just calling it like an algebra equation, right? The slope. Okay. So here, I'll give you guys at least one step. Guys, can I take that square root g and slide it over underneath the 2 pi? Make this 2 pi divided by the square root of the gravity field, and then times the square root of the length. This and this are the same thing, isn't it? Is it? I just shuffled the gravity field over a little bit. Okay. Now, guys, could you graph t versus the square root of L, and then the slope of that line would be this funny looking fraction right here? And you could eventually solve gravity that way, couldn't you? Okay. No, since we're all in one class, all working on the same thing together, but I'm going to go a few more steps and do something a little different. Okay? A different way. Okay, there's probably like 5 or 10 different ways to do this, okay? To linearize this graph. Can you linearize this in such a way that the gravity field is exactly equal to the slope of a line? Because right now, well, it's not exactly the gravity field. It's 2 pi divided by the square root of the gravity field. You kind of get it from there. Okay? But can you rearrange this a few more steps to make the gravity field exactly the slope? So you have something in the form y equals mx. How could you do that? Right now, the gravity field, well, there's 2 problems. One is that it's a square root. And the other thing is that it's in the denominator. So let's get it out of the denominator. How could you do that? Yeah, cross multiply. Let's do it. So I could say 2 pi times the square root of L equals the square root of G times the time period. That's okay, right? I just cross multiply the G. Okay. But it's still square rooted. So that wouldn't tell me exactly the gravity field. Like the slope of the line wouldn't be exactly the gravity field. It'd be the square root of the gravity field. So how do I undo a square root? Square both sides. As long as I square everything, it's still valid, right? So let's do 2 pi quantity squared times L equals gravity field times time period squared. Ah, do you guys see it now? See what we build up to? This is like your y-axis. This is like your x-axis. And the gravity field takes the place of the slope. Okay, see it takes the form y equals mx. Okay, see it? Okay. And that's why I had you guys set up 4 columns in this table. Because we haven't done anything in these last 2 columns. What do you think I'm going to write in these last 2 columns? 2 pi quantity squared L. That could be in meters. And what goes in this last column? Time squared. That'll be in square seconds. So, okay, so we do have to calculate all this. Okay. Yeah, I know this is kind of a funny long process, but this is like right up AP's alley. This is like exactly the way they would ask you this question. All right, so let's do that. Let's take 2 pi quantity squared. Make sure you got parentheses around the 2 pi, so it's squaring the whole 2 pi. Okay. And then times each one of these lengths. So times 0.1. This works out to about 3.95, and I put the unit meters. I embedded that in the column head. All right, let's do 0.2 here. This is about 7.90. Let's try 0.3. This is about 11.84. This is about 15.79. And the long pendulum is about 19.74. Right. That's yeah. Okay. Well, it's meters, but it's weird manipulated axis unit or axis, right? Because it's 2 pi quantity squared times the length. Unit would still be meters. And then last column, square all the time periods. Okay. And maybe you ran the experiment yourself on this mystery planet. Right? So you've been timing all these pendulums. And so we have all the time periods. I just have to square them. What's that? 24 squared. This is 0.71 it rounds to. Right. 1.19 squared. This is about 1.42. These are all square seconds. I put square seconds in the heading. 145. This is 2.10. This is 2.82. This is 3.53. All right. So let you guys catch up to this. All right, you guys are writing all this in your notes. All right, while you guys are digesting this, give you guys a review so far. Okay. All right, so you landed on some mystery planet. Okay. We don't know what the gravity field is, but we're going to find it by swinging a pendulum. Okay. So I have 5 different length pendulums. They go from 10 to 50 centimeters. Okay, so they're all short, long, they're all different lengths. Okay. And I time them with my space stopwatch, and I get all these different times. Right? Yeah, the longer the pendulum, the more time it takes to swing. That makes sense. Right? And there's a few different ways to get the gravity field out of this. What we're going to do is we're going to make a graph. We're going to a linearized graph, and we're going to take the slope. And we've done the algebra ahead of time. That's over here on the left side of this paper. And we've set this up in such a way where y equals an x, where this will linearize. All this data will linearize, and the slope of this linear graph will exactly represent the gravity field of the planet. Okay, you guys get that? Okay. So graph time. You guys ready to make a graph? Let's make this graph. And so we just need to plot these last 2 columns, y versus x here. So on the vertical axis, it's going to be it's going to be right here. It's 2 pi quantity squared L. So let's do 2 pi quantity squared L. This will be in meters. Okay. And it looks like it goes up to 19.7. Let's call it 20. Let's go 5, 10, 15, 20. So 0, 5, 10, 15, 20. Then the horizontal axis is going to be time period squared. It's right there. So put time period squared. The unit is square seconds. Now that goes up to 3.5 something. I'll call it 4. Let's go 1, 2, 3, 4. So 0, 1, 2, 3, 4. Okay. Let's plot all these points. Okay. I'm making the claim that all these points are going to line up in a straight line. Let's see if that's true. Okay, so graphing. Oh, yeah, I can fit them right here. Okay, so for the time squared, it'd be 0.71, just right about here. The 2 pi quantity squared L is 3.95, but plus 4 is right about here. Bam. So then I got a point on the board. Okay, 1.42 right about here. That's going to be 7.9 is right about here. It's almost 8. It's right about here. Bam. 2 points. 2.1 right about here. 11.84. It's almost 12. It's probably right about here. Bam. 2.82. 15.79. 1570. That's where it is. Bam. And 353. And then shade less than 20. Bam. Oh, yeah. Look at that. All those points. Zip. Straight line through the origin. And remember, the slope of this line represents the gravity field. You see that? Right there? Yeah. So, last thing. Okay, here's the coordinates for each of those 5 points. Here's how they map out on a graph. Okay. Somebody tell me, what's the gravity field of that planet?
This is 5, yeah. 5.6.
Yeah. 5.6 meters per second squared. That's the gravity field of that planet that we just landed on. Okay.
This one.
All right, you guys see that?
Oops.
All right. Okay. So I know I only got so much class time. I always try to hit some fundamental examples with you guys, but yeah, look for something like that on the AP exam. That's the kind of skill set that you have to have. Okay. So let you guys go study that. All right, moving on. All right, so remember this one. You guys saw this one about last couple minutes of class. Okay. Yeah, suppose I have a block on a spring bounce up and down. Okay, and another one going horizontal. Okay. I meant to mention this detail before, but guys, if these are the same mass springs, or sorry, the same spring constant spring emit, and the same masses on them, okay, do they both oscillate in the same time period? Yes, they do, and you could back that up with this expression right here. Okay, this right here. Right. What about this? Because what if you had a vertical one and you moved it from Earth to the Moon? Okay, it's going from the Earth to the Moon. Does it take more time, less time, or the same time to bounce up and down? Same time. Yeah, because gravity field's not in this equation. Yeah. Right. Now, this horizontal one, they might say put an air hockey table here that has no friction. You guys see that? Like a frictionless surface. So it just goes horizontally. Okay. This tells you the east-west component of this car going around in a circle at constant speed. And this vertically bouncing one could read you like the north-south component. Okay. Okay, now they're all like speeding up and slowing down. But what's going to turn into is like a cosine curve and a sine curve. Doesn't cosine tell you on a unit circle how far right left you are? And sine tells you how far up down you are? It's cosine and sine. Okay. And so we're getting towards these graphs. Here's another detail. Guys, how do you read this again? Frequency is 1 over the time period. Okay? And then time period is 1 over the frequency. Okay, so these are reciprocals to each other, time period and frequency. Let's do an example. Maybe you have a pendulum. And if the pendulum takes 1 second to swing back and forth. You guys see that? It takes 1 second. Half a second one way, half a second the other. It takes 1 second to cycle. What's the time period? 1 second. And what's the frequency? 1 hertz. Because hertz is like cycles per second. Okay, so 1 over 1 is 1. Now, what about this? What if you go to a planet with a very strong gravity field? And you take out the same pendulum, very strong gravity field. You go, do you guys see it doing that? Okay. Suppose it cycles back and forth 10 times in a single second. It's going so fast. 10 times in a single second. What's the frequency?
0.1.
10 hertz. This frequency is 10 hertz. But how much time does it take to cycle once? 0.1 seconds. You guys see 10 hertz, 0.1 seconds? Correlate? Guess that? Right. How about this? What if you go to a really small asteroid with a weak gravity field, and it takes 10 whole seconds for this to cycle all the way around? 5 seconds one way, 5 seconds the other way. It takes 10 seconds. Do you guys see that? It takes forever. The gravity field is so weak. It takes 10 seconds. What's the time period? 10 seconds. Therefore, what's the frequency? 0.1 hertz. Do you guys see that? This is like 0.1 hertz going on right here. Okay. This is like 10 hertz. Is that? Okay. Now, how about this detail? So I know omega, last few weeks we've been calling that angular velocity, but that's not what this is in this context. It's called angular frequency. All we're going to do is take the regular frequency, like 1 hertz or 10 hertz or however many hertz. We're going to multiply by 2 pi, and that's going to allow you to create all these graphs I'm about to walk you guys through. Okay, you guys ready for that? Sorry? Okay. Again, these could apply to either the lateral position of the bob on the pendulum or the vertical position of this block on the spring. Okay. So either scenario, here you go, same 2 scenarios. Okay. Now here's why I'm multiplying by 2 pi. Okay. Because here, let's do the example of 10 hertz. Okay, so it's called like guess that? It's oscillating at 10 times per second. Okay. If it's 10 hertz, what's the time period again? 0.1 seconds. It takes only 0.1 seconds to oscillate back and forth. Okay. Right, so let's look at this governing equation. Position as a function of time. Right? That t is the time it's tick tock. Now, if you take that frequency of 10 hertz and multiply by 2 pi and plug that in right here for this omega, for angular frequency, and then you allow exactly 1 cycle to go by, which you guys just told me is how much time again? 0.1 seconds? Okay. Guys, what is 2 pi times 10 times 0.1? Here, I'll write it down.
It's 6.2.
Yeah, it's 2 pi. Yeah, 2 pi times 10 hertz times 0.1 seconds. Well, this just cancels out, and it leaves you with 2 pi, doesn't it? Yes, yeah. In fact, for 1 complete cycle, doesn't the frequency and the time period always just cancel out? Okay. And it leaves you with 2 pi. On a unit circle. Because how many radians does it take to go all the way around?
2 pi.
2 pi. Right? 2 pi radians to complete a full cycle. That means from here to here, you would have gone from cosine of 0. What is cosine of 0? 1?
1.
Okay. What's cosine of 2 pi?
1.
Also 1. And you're looking at it right there. You guys see that section right there? That's one complete cycle. You guys see that? That's why all this stuff. Okay. All right, and then you can just have some generic time, and it just keeps on going on for oscillates back and forth. What do you guys think that A stands for? So where that starts with A. Amplitude, which is this just from here to here, right? So if this was like 5 centimeters, or if this was like 5 centimeters, this could be 5 centimeters, right? Right. And maybe the total motion could be 10 centimeters, could be 2A. Is that? But the amplitude is just defined as that, right? So we got that. Right. Now, I'm looking at something that reminds me of kinematic days. Do you guys see position versus time, velocity versus time, acceleration versus time? Right. These are all related to each other. Once you know position versus time, you can get the other two. You can derive the other two. Ooh. That almost sounds like a calculus word. Guys, what's the rate change called in calculus?
Oh.
Okay, derivative. Yeah. Which is like slopes, derivatives. Right?
What?
Yeah, it is related to slopes. Because guys, what's the slope at the peak right here? 0? Like, couldn't you just stand on top of the sill? There'd be 0 slope just for one instant. Okay? And that said correspond to 0 speed. Is that true? 0 speed? Oh yeah, zero slope here is 0 speed here. Right? Or another way to say that is when you pull this back and you're just releasing it, you are releasing it from rest. You guys see that this maximum displacement here corresponds to releasing from rest here? You guys see that? Right. Hey guys, what's the rate change of cosine called from calculus? You have to be in calculus to know this. What's the rate change of cosine? Negative sine. Right. What's the rate change of sine? Is cosine, and since it was negative, it just stays negative there. Right. And one more detail is you guys see this angular frequency? Every time I take a rate change, another angular frequency comes out. Right. There's an omega here and then omega squared here. Right. And what rule is that called in calculus? Starts with the CH. Chain rule. Okay. Now, big equations, they give you one of those. They just give you amplitude times cosine of 2 pi. Actually, they even put in the 2 pi times the regular frequency and then the variable time as a position. You guys see that? Okay. Now, if you started somewhere else, like if you let's just start swinging and you started your time interval when this was just going through the bottom, then this cosine curve would become a sine curve, and that's why they also threw in the sine. Okay, good. You guys see that? All right, so physics going on there. All right, what's we got for you guys? Oh, oscillation linearized. Okay, so this is, guys, these look pretty similar to the notes we were just doing a few minutes ago. I'll walk you guys through the whole like table. We were trying to figure out what was the gravity field on some weird planet. Right? Now this looks like a little bit different solution. Guys, you could do t squared versus L. It'll still linearize. Guys, look up here. Here, sit down. Look here. Okay. It'll still linearize. In fact, this is looks like the graph that we put together yesterday. Right. But the slope is not exactly the gravity field. It's equal to this fraction. Now, you could still solve it this way, but whatever the slope is, you set equal to 2 pi quantity squared over g, and then you could solve for g. You could do that way. Okay. Or if you have the mass and spring, very similar. Okay. All right. Oh, I think I showed you guys this one before, but let's hit this again anyway, because this is worth our time. So here's the scenario. I'm going to take a... Here, guys, look here. I've got this spring hanging from the ceiling. It's got some spring constant, and right now there's nothing on it. But I'm going to hook something on it. I'm going to hook this right here. Now, if you see the question phrased this way, you put your hand right here, and you slowly lower it to rest, to equilibrium. Is that going to be this middle picture? Right. And if they ask a question like, how much does it stretch? Guys, how can you set that up? What's the framework in physics to find the equilibrium stretch? It's not 1/2 kx squared. F equals kx. It's Hooke's law because it comes from force equilibrium. Isn't it true if it's just hanging out at rest, the sum of the forces is 0? So we got mg down, we got kx up, right? And it has to 0 up. So you could solve for x, and it would be mg over k. Okay. Right. Now, what if I change the premise a little bit? So I'm going to go back. I'm going to hook this on this spring. But instead of slowly lowering it to rest, instead I'm just going to drop it. It's going to overshoot the equilibrium and start just oscillating. You guys see it? So what's the maximum it would stretch from? Okay, you guys see it? And to solve for the maximum stretch, you don't use equilibrium because that's not equilibrium. That's what framework in physics? Yeah, conservation of energy. You guys, what type of energy right at the very top? Just as I'm hooking this on. gravitational potential. Is that called MGH? Right. Now, if the lowest point, if we call that height 0 at the lowest point, then the H is X max, wouldn't it be? Right. Then, when the block gets down to maximally stretching the spring, where'd all the energy go? Into the spring, and there's your 1/2 kx squared. Okay? Now you can still solve for x, and then you can do a comparison. Do you guys see what the ratio is? 2 to 1. You guys see this is this by a factor of 2, right? Right. So, guys, pretty soon when you guys get this lab, guys, look up here. Think about this. When you guys eventually get this lab, I'll give you guys some springs, some weights. Okay. If you slowly lower it to rest, suppose it lowers to rest to like 10 centimeters. I'm just making something up. Guys, if this is 10 centimeters, you go back and you drop it. How far do you expect it to drop? Pretty close to. I bet it'd be pretty close to 20 centimeters. Right? You can see that for yourselves. Right. All right. Now that's all the oscillation. I have some wave stuff for you guys. Again, this is a little bit bonus because a few years ago, AP used to ask all these questions about show guys. They dropped all these questions, but anyway, good to know stuff before you graduate. Right, so let's look at waves and properties of waves. Right, so a wave, okay, we've got some kind of oscillating motion. Right, we've got frequencies 1 over time period. Okay. Next here, what else we got? Do you guys see from crest to crest? Could be like 1 unit of the wave. Okay, so we'll define that as 1 wavelength, and we're going to call it. Guys, what Greek letter is that? Lambda. Lambda. It's Greek letter lambda. Okay. Now you don't have to go crest to crest. You go trough to trough. You could go, ooh, how about 1 full S shape? Guys, is 1 full S shape also 1 complete wavelength?
Yeah.
Right, it's all the same length. Right. Okay. Now, because what if you do ocean waves? Can you guys see some ocean waves coming in?
Yeah.
Right. And what if you measure from crest to crest? Like, okay, it looks like it's about 10 meters, let's call it. You guys see 10 meters from here to here? Right? You're watching these ocean waves come in. It's 10 meters from crest to crest. Right? And you also see that they're hitting the beach, let's say, every 5 seconds. Okay? It takes 5 seconds to hit the beach. Guys, if it takes 5 seconds for every crest to hit the beach, what's the time period? 5 seconds. Right? What's the frequency? 1 over 5 seconds, which is 0.2 hertz. You guys see 0.2 hertz?
Will we have any more take-home quizzes this year?
Huh?
Will we have any more take-home quizzes?
I'm gonna do this next one in class. So 0.2 hertz. All right, now guys, let's go down to this equation down here. So we've got the wavelength was 10 meters. Is that right? 10 meters. And we got the frequency is 0.2 hertz. Guys, what is 10 times 0.2?
5.
What?
Point or 2.
2. Okay. 2 what? What do you think V stands for? Velocity. Guys, this is 2. So what are the units? That's 2 what? Meters per second. Meters times hertz, so it's meters per second. Okay. What did you just find? You just found how what? How fast the waves are coming in on the beach. You guys see that? Okay. So wave formula right there. Okay. All right. So categories of waves. So there are 2 main categories of waves having to do with the motion. So one category is called transverse, another is called longitudinal. Okay. So what makes something transverse is if the motion of the particles, up and down in this case, is perpendicular to the propagation of energy, which would be left to right. But if it's longitudinal, then all these little molecules might be moving right, left, and the energy is also propagated left to right. So that could be like a parallel configuration. Okay. Okay. Let me show you guys this in animation here. Okay. So do you guys see transverse, longitudinal, something like that?
The longitudinal.
Yeah. Yeah. Let's do this. What do you guys think?
Which one do you
What do you guys think sound is? Like as you're hearing me right now. Actually, let's go back to this one.
Longitudinal.
Yeah, sound waves are longitudinal. So if you can see all the air molecules vibrating between me and you, yeah, it would look like this bottom picture, longitudinal. Right. What do you guys think light is? Yeah, and let me show you guys that that's true, that light is transverse. Right. So, here, this guy's going to show you. There's transverse. There's longitudinal. Okay, so we have transverse, longitudinal. Got some definitions mapped out. Okay. Now he's going to bring in a polarizing filter. Now, if something's polarized, it only allows waves through in one direction. You guys see that? It's putting some crazy wave, but he's only getting the horizontal components. Right? So if he does horizontal, yeah, it goes through. But if he does vertical, nothing goes through. Right? And if he does something crazy, then only the horizontal goes through. Right? So let's see. If light was polarized, then right, then it could be shown to be have transverse properties. At least that would be evidence. Right? So he's got some polarizing filters that only allow light through one way. Guys, see if they're lined up the same way, like horizontal, horizontal, the light gets through. Right? But if he rotates them, right? Oh, because now they're the same way. Now they're 90 degrees to each other. Right. Let me show you guys that in class here, because I have some polarizing filters. Actually, you might have some polarizing filters also. If you have some sunglasses, if your sunglasses are polarized, if you take two pairs of polarized sunglasses, you can do what I'm about to do right here. So if this is vertical and vertical, okay, so a lot of light gets through. What if I rotate one of these? Oh.
Oh my goodness.
Because vertical and horizontal, no light gets through.
Is it?
So that's evidence that light is a transverse wave. That's one way to show it. Alright, so what else we got here? Ooh, let's do interference. So you guys see wave pulses? Now, that's a good picture, but it's better to see these in motion. So I pull these in motion here. Constructive interference. You guys see those two wave pulses? Let's call it 10 centimeters and 10 centimeters amplitude. Guess what happens when the 10 and the 10 cross?
Okay. 10.
Whoa! Made 20.
They said they go through.
You guys ready? 10 and 10 is 20?
Yeah.
Whoa. And they do pass right through each other. That's pretty crazy too.
How'd they do that?
It's called interference, constructive, destructive interference. So now you're going to see destructive interference. You guys see a positive pulse here and a negative pulse here? What's going to happen? Oh, they cancel out. Oh, then they keep going through each other. Whoa! And watch this one reflect upside down. Boing, reflects upside down. Ooh, pretty cool. Now, let's see that one more time. All right. So we got a positive pulse and a negative pulse. As they're crossing through each other, they cancel out. But they do keep on going. Keep on going. Yeah. Right. Who's ever worn noise canceling headphones? Okay. So basically that process. No, sound of course is longitudinal, not transverse like on the screen right here. But noise canceling headphones will actively take all the high and low pressure points of sound and reverse them and mix them. So it's destructive interference. Right. Let's look at some standing waves. Standing waves. So standing waves are points where there are these nodal points that don't move at all. So that could be a half wavelength. There's one wavelength. Isn't that one full S shape, one full wavelength? And there's a node right in the middle. You can touch it right in the middle. It doesn't actually affect it. But you can create different standing waves. Right? Now, we can take that and do some fun stuff with this. Right. Let's look at Chase from California here.
My name's Chase, and I live in California, and I'm gonna try to break this wine glass by only my voice. Mom, look. Look it! I did! I broke the glass!
All right, so do you guys think that that glass has some circumference on it? Some circumference?
Can we watch the rest?
Well, he has a has a broken glass, so safety reasons. Right? But guys, there's some circumference on that, isn't there? Right? Now, if he gets just the right frequency going, there's some associated wavelength. Because you guys know every musical note is like a frequency associated with it. Like one of the A notes is defined as 440 hertz. Right? All right. So if there's some wavelength that matches the circumference of that glass, and he keeps pumping in that same frequency, that it's called a resonant frequency. You can tear that down. Okay? Guys, how many of you guys in ROTC? ROTC. Okay. Do you guys learn how to march in step, left, right, left, right? Okay. But where are you specifically not supposed to march in step? Or is it no break step and just walk regularly? A bridge? Why a bridge?
It'll vibrate.
Yeah, if you get the resonant frequency, it's kind of a small bridge. Might get dangerous. Let's look at a very famous bridge collapse from 1940. Right, so they're building this bridge. Right. Now this bridge did bounce up and down a little bit, and it was in operation for a few months. Right. But one day, it's like November 7th, 1940. Oh, whoa. Right. So this is out in Washington State. There was this crosswind that was blowing, steady crosswind. Right. Guys, what is that bridge made out of? Concrete and steel? Yeah, concrete and steel. Oh, but they did something wrong. Right? Now, guys, if you look at the time period of oscillation, you might count off about 5 seconds. About right? Guys, if the time period is about 5 seconds, what do you think is the resonant frequency of that bridge? 0.2 hertz. 0.2 hertz. Yeah. Right. Maybe if you had like some oscillating machine, it was like 0.2 hertz. I do something like this. Yeah. Let's see what happens.
Well, I did take. I mean, both cut it out.
Well, car go. Why did a car go?
They sent an engineer out there to check it out. Yeah.
Hey,
Oh, he got off. He got off.
Oh, well, there it goes. I was on my bridge station.
Yeah. And sometimes I would pause this right place. You can actually see what they did wrong with it. It's right up here in the span. Right. So yeah, let's look at what went wrong, and they did go back and they rebuilt it, and they made it actually work. Right. So what was wrong with the original design? Right. So what they were thinking was, well, we're gonna have all these here, guys, think about this. We got all these heavy cars going across the bridge, and the best support for a vertical weight would just be these vertically oriented girders. What they're thinking. Let's make it really strong vertically. So we've got all these vertical girders. You guys see all these vertical girders? Right. But guys, all that vertically oriented girders, does that have any horizontal strength? Hardly any at all. So when you get a horizontal crosswind, right, now the bridge is going to fall apart. You guys just saw it. Right? Now, all they did, the columns were fine. Those big old column towers that were holding up the bridge and the suspension bridge, like those were fine. So all I had to do was go back and rebuild this road. Right? But they said, okay, well, obviously let's not go with the girder design because, well, it didn't work out last time. So how do you think you fix this? Very simple fix.
Oh, the truss.
Yeah, truss system. Yeah,
Truss.
just go put in a truss.
I did it, Mr. Chris.
Yeah.
Super cool.
Yeah, right. And now you get the vertical strength, but also the lateral strength. Yeah, truss system.
Wait, so is that like the polarized stuff?
I think something a little different. I don't know. Might be a connection. All right. So there you go. I saw the bridge. Ooh. Let's look at guys. If you have these patterns of construction and destructive interference, you guys saw those. Right? One thing that'll mark out waves and wave properties, like how do you define something as even being a wave at all? Right? Because that was a question for hundreds of years: is light even a wave? Right? Is if something creates an interference pattern? Well, so here you go. Let me get light top to this. Alright, so inside here, I got a little pool of water. You guys see a little pool of water right here? Right? I got this plastic arm that's reaching over. It's gonna just touch the top of the water. And let me show you guys from the side what this looks like. Right. Looks like this from the side. You guys see that? Right. See this bit's gonna reach out and just touch the top of the water. Right. And this little nozzle right here, guys, listen. You guys hear? Ooh, I can feel this thing vibrating. So when I put this arm back on, vibrate the water. Okay. And you can only see it if I put the cover on. Okay, guys ready? Ooh, so some rays. Okay. I see a wavelength. I can hear a frequency. Guys, listen real close.
I hear it.
You guys hear that buzzing going higher frequency, lower frequency? Hey guys, if I turn up the frequency, what happens to the wavelength? Gets shorter. Huh? If I turn down the frequency,
it gets longer.
It's longer. Yeah. How about this? Got a lot of.
I did it.
Let's take this guy out.
Right.
Let's replace it with this guy right here. See that?
Be two different.
Yeah. Are you guys ready to see some wave interference?
Yeah.
So that's gonna look like.
Constructive or destructive?
Well, it'll be both, right? Because here, it's based on this. So this is pretty much what you guys are gonna be seeing. You could have constructive, destructive, constructive, destructive. It's like it oscillates. So it's like bright, dark. Yeah, because you got this whole interference pattern going on. So that is. Yeah, there you go. Shear interference pattern.
So cool.
Very good. Good. All right, let's get that over. Okay, get lights. Ooh, lights. Let's see what else we got for you guys. Okay. I do have a few more of these that I want to do with you guys. This will be a lab I'll have you guys do in a few days. But since I got so much time, let's finish class with this. I talk about earthquakes a little bit. Okay, so ooh, hey look, we're back to transverse and longitudinal, but it's not called transverse longitudinal. You guys see S and P, right? So P could be primary waves or pressure waves. S could be secondary or shear, right? Both those, right? Guess which waves travel faster, the primary or the secondary? How about the primary? They hit you first. Okay? Let's see what this looks like. And which do you think are more destructive? How about the shear waves, the secondary waves? Right? And so here's a famous earthquake from about 15 years ago. Right, so, oh, there's the P waves. Do you guys want to be swimming around that water? Hey, the P waves are hitting us. The water's still nice and calm. Let's jump in the water. Let's go for a little swim. Oh no! What is that? It's S wave time.
What now? What is going on? It's an earthquake. What's an S wave?
Secondary wave.
Yeah, there's your S waves right there. So that's those. Yeah, it's big ones. Right. So, guys, let's talk about measuring earthquake spin.
So don't go in the.
So, yeah, don't go in the water. It's a lesson. So, guys, all over the world, there's these seismic stations. There's these rolls of paper, right? And you got a big old mass pin, a lot of inertia. It's on a big old spring. Right? And all day, every day, it's recording a very boring flat line. And this roll, whoops. Sorry, I switched my screen. Here we go. Right. So, guys, you guys see this roll of paper? It's rolling all day, every day. Just rolling. Right. Here's a pin with a big old mass on a spring. Right. Creating a very boring straight line. Okay. Until an earthquake hits and the whole earth vibrates, except for this very large inertia on a spring. That stays relatively still. And then what you get is something that looks like this right here. Right? Here's your P waves. Here's your S waves. Right? And guys, if you know the time delay and how fast this wave travels, can you figure out how far away the earthquake is happening?
Yeah.
Okay. And then if you have a bunch of seismograph stations and you draw radii around each one and say, oh, happens this far away, happen this far away, happen from this guy, maybe this far away. You can't find the epicenter. All right. So more physics tomorrow.